All right, so we're gonna look real quick at work energy, and only half of you have kind of seen the lesson yet, but hopefully you can look at this soon. So basically, in the last section in force acceleration, we kind of heavily relied on the equation F equals ma, right? Because we set all the forces acting on a body equals to the mass of the body times the acceleration that it undergoes in a certain direction, right? So if you integrate that, you're able to find different quantities. You're able to relate work and energy, right? So if you integrate force, you get work. If you integrate mass times acceleration, you get energy, right? So basically what happens is you get an equation that means that says the work is equal to the change in kinetic energy of the body, which means work is final minus initial kinetic energy. And then you get your work energy equation, which is the pink one right here. That says the initial kinetic energy plus the work done on the body equals the final kinetic energy, right? Usually you'll be given initial kinetic energy and you'll have to find the equation, or not given kinetic energy, but you'll be given the mass and the velocity, and then you'll have to translate that into the energy, and then you'll also have the information you need to set up the work equations, and then you have to probably end up solving for either the final kinetic energy or the final velocity, right? So work isn't just done anywhere, right? So obviously if we integrated with respect to position, this quantity has to be somehow related to changing a position, right? So basically any force that changes position is going to cause a work to be done, right? So weight changes position because if I hold something above the ground and let go of it, the weight will obviously cause it to move. Springs will cause a change in motion because they'll suspend something. Friction will, this one's kind of tricky, but this one causes a change in motion because it essentially adds a negative velocity to, because you know how friction works in the opposite direction of motion, right? So it's basically adding a negative motion. Applied forces in a couple moments, of course, the only like reason to apply a force is if you're trying to move something. So those all make sense. Normal force does not cause motion. All it does is prevent motion. So that's not going to cause work. Pin reactions don't cause work because again they prevent motion. And then friction on a no-slip wheel does not cause work because the wheel is not actually showing friction. So these are the screenshots of the notes that Dr. O'Neill posted to the original Canvas page under the videos, but I thought they were pretty good descriptions of the concepts, so I used them. So the work done by weight, this is the equation for it. You only have negative W or negative weight times change in Y on your reference card. So your job is to understand how this is equal to this, right? So basically, obviously, this is the work done by weight. It's going to be the magnitude of the weight times whatever change in height there is. So this is going to be H1, and it doesn't matter what the heck path it takes to get to its endpoint. You only care about the difference in the heights. Work done by friction, again, you're only given this equation. You have to be comfortable getting it from here to here, but that's pretty simple. All you have to know is that friction is going to be mu sub k times n, and the distance is just going to be the final position minus the initial position. So again, you have the friction force going opposite the direction of motion. That's why it's negative. And then mu sub k times n, and then the position here minus the position here. That's your equation. Springs are probably the most tricky one because you have to deal with this term equaling this term, right? So you get this equation on your reference card, right? And you also get that, for example, S2 equals L2 minus L naught. But basically what that means is that you have to measure everything with respect to the initial spring length, right? So if you don't, you're going to be measuring it from, say, whatever this wall is to over here, right? Which doesn't make any kind of sense because then you have some kind of arbitrary value. So you can either intuitively know that the position from the initial length onward is S1, so you're squaring this distance, or you can say that you know that S1 is the difference between the stretched length and the unstretched length, right? So that's up to you. They're equal to the same thing. I personally would do it this way just so you can double check your work, but you still do final position. So basically you're going to have three positions here. You're going to have an unstretched length, that's L naught, right? That's essentially you zeroing out the stretch. Then you're going to have some kind of stretched or compressed position 1, and then a further stretched or further compressed position 2, right? And these are the two that you're relating, but you're relating those lengths with respect to this unstretched length. So that's something to practice and get used to, because it's kind of easy to forget that you have to subtract that initial length. So the last two are applied forces and applied couple moments. Again, obviously these should be included because of the entire purpose of applying a force being to generate some kind of motion. So if you have a constant applied force, that means it's not dependent on any other variable, right? So it's just a magnitude. So you can take the magnitude of that multiplied by a cosine theta, assuming that the cosine theta describes the direction of motion in the x direction, right? So here in this example, we would take 5 times 3 over 5, right? But then on your equation sheet, you get cosine theta, I believe. Actually, I don't even know if this one's on your equation sheet. That's something to look at. But basically, all you need to do is understand that this term is the magnitude of the force in the direction you care about. And in this exact example, we're talking about a change in position in the horizontal direction. So we want the force in the horizontal direction. So that's if it's a constant. This one is dependent on S, so we would need to integrate it between the initial position and the final position. So this would be S1, this is S2. And then again, we only care about the portion of it in the x direction. So that could be cosine theta, or that could be 3 over 5. This is essentially the exact same situation, but with couple and theta, right? Because couples cause rotation. Theta is essentially the S equivalent. So yeah. Two more equations to know is that kinetic energy. You should know this already from physics 1. I know they stress it a lot, but kinetic energy is 1/2 mv squared, right? So the initial kinetic energy is going to equal the initial velocity, and the final kinetic energy is going to implement the final velocity, but other than that, they're the exact same formula. The last slide I really wanted to talk about was exactly what steps you need to do to solve these problems. The first two are the exact same as normal. You classify the motion and determine what properties you're given. And then after that, you calculate work for each component in the system. So if you have a spring in a box that has friction, you need to sum the work of a spring, sum of the work of a box, and weight if it's changing position vertically. So in that sense, you'll have 3 values for work, assuming that this spring is, say, pushing that box up a hill. So you'll have 3 values of work, and then you add them up, and that's what's here, the total work done on the body. The next step is to calculate the initial energy, which is the value here. That's 1/2 mv1 squared, so the initial velocity. If it says it's from rest, this whole term goes to 0 because the velocity is 0, which means you're going to be squaring 0, multiplying it by 1/2 mass, which just means it's 0. And then basically you solve this equation for whatever quantity it's asking you for. You just have to be careful what it's asking you for, because sometimes it'll ask for the kinetic energy, sometimes it'll ask for the final velocity. And again, this is just an office hours reminder: Monday, Wednesday, Thursday, 5:30 to 6:30, and Tuesday, Thursday, 9:15 to 10:15. All right, I hope you all have a good week.